Hi all, this is Mr. Yeager for Physical Science. We are looking at the topic of magnetism, which is not a very long topic in physical science. We're really looking at just basically what is it, what's it caused by, looking at the magnetic force and how objects will attract or repel with magnetism. And then we look a little bit at electromagnets and the use of electromagnets. So here we go. All right. So magnetism itself, all right, is the attraction or repulsion due to the arrangement of the electrons. Okay, attraction or repulsion due to the arrangement of the electrons. Now we don't have to get in too much detail about this, but basically the idea is electrons can spin two different directions when they're inside the substance. So they can either be spinning clockwise or they can be spinning counterclockwise. When we show this in substances, we basically just like say, clockwise is left and counterclockwise is right. And in a substance, electrons are pointing different directions throughout the substance. Okay? Now, if something becomes magnetic, though, it's because it turns out that every single one of those electrons is spinning in the exact same direction. Okay? Or at least the majority, or many, not just majority, but like 90% of them are pointing in that direction. When you do have some going the opposite way, that will decrease the magnetism, and it can possibly slowly reduce the magnetism because they are running into each other. But if they're all spinning the same way, this is what causes magnetism. So that's what we mean by arrangement of the electrons. Okay? So, with that in mind, if an object is able to do that, we call that a magnet, and that is something that is then able to attract and repel metals. Okay, metals are our primary magnetic substances, and that's because they have these loose, delocalized electrons. All right. The magnet itself is usually a metal. It's possibly made of something else, again, because you just got to have those electrons moving. But the thing is, certain elements, certain compounds, they hold their electrons better than others, and it's tougher for them to basically turn into a magnet. Okay? So, with that in mind, a magnet creates what's called magnetic force. Again, any force is a push or pull from the magnet. It turns out when you decrease the distance between magnets, you'll increase the force. Okay? So there's an inverse relationship where if I want to increase the force, I decrease the distance between the two magnets. And again, if you've ever played with magnets, you see that. If you hold them really far apart, there's no attraction. But as they get closer and closer, eventually there's a point where you get them close enough and they'll attach very quickly, like these two down here. Okay? So the distance between them, if I decrease, I increase the force. So there's an inverse relationship between force and distance. Magnets have two poles. They have a north pole and they have a south pole. Okay? And again, that's just kind of showing which way the electrons are spinning. I'm not going to say, because I don't remember which way we would say that the electrons are pointing, but basically we have a north and south pole created on every single magnet. Every magnet has a north and south pole. You cannot have just one pole alone. All right? So, when we have these poles, like poles will repel. So north repels north, south, and it's not on there, but south will repel south. They will repel each other. Okay? So like poles repel, just like charges repel. Unlike poles attract. North attracts south. Okay? So it's the same exact thing as charges. And here's what I was saying, where every single magnet has a north and south pole. If you break a magnet, it turns out that you will form two smaller magnets with a north and south pole. So sometimes I get some people that question this, where they're like, well, what if we cut this one in half? Then I have a south pole and a north pole. What will happen is the northern part of that southern magnet, if you want to call it that, will become north, and the bottom part of the northern pole magnet will become south. So they do continue to be magnetic. Okay? So like poles repel, unlike poles attract, opposites attract, and we can continue creating more magnets if we break them. Now, they will get weaker. Okay, you have less electrons, they will get weaker. Now we brought this up in electricity. There is an electric field. There's also what we call a magnetic field. All right? This is an area around the magnet where the magnetic forces are detected. All right? And you can see my picture below right here. Come on, thing. All right? My picture below right here. All right? These are invisible lines around the magnet. You don't see the magnetic field. All right? But when you put a metal close enough to the magnetic field, what's it going to do? It's going to attract and immediately start being pulled toward that magnet. All right? So that's what's going on with the magnetic field. It's this invisible field going on around it where it's a sphere of influence. As you get closer, it gets stronger. It gets stronger. Now, one major point to notice on the drawing here is that the magnetic field lines come out from the north. Okay? Field lines come from the north, and the field lines go to the south. Field goes to South Pole. All right? So you can see how this is drawn. The field lines are always pointing out from the north. Technically, this one would go around and then come back in at the South Pole. So field lines always point away from the north, always point towards the south. All right? As how it's always drawn. So if I draw one up here and I don't put the poles, and I draw it like this, where it's coming out from that side and then going into that side. That means this left side over here must be the North Pole. The lines have to come out from the north and go into the south. So pay attention, because that is one of the common questions on EOC of understanding which direction the field lines go. Always from the north into the south. Okay? There you go. Always drawn north to south. So this is why we get some attraction. All right? What happens with this is the pictures I have drawn here. Let me see something real quick. Yep, okay. The pictures I have drawn here is, right here, this is a north and a south pole. You can see the lines are going straight at the South Pole from the north. This is why these two poles attract. All right? This is basically saying the north wants to go to the south. They want to go straight at it. It wants to attract. But if I put two north poles together, like poles, look at what the field lines do. They push against and away from each other. All right? So this is where we got repulsion. These two poles are being repelled. Same thing goes for south poles. All right? They're both pulling the lines in, and those lines would push against each other because they're both fighting for those lines. All right? So this is showing how these field lines work and why they create some attraction between unlike poles and repulsion between like poles. So you've probably, maybe we don't actually, I guess most people don't use them as much anymore, but if I guess you're a big hiker or you're a Boy Scout or Scout in any sense, all right, you probably have used a compass. And a compass is always following Earth's magnetic field. Earth itself is a giant magnet. All right? Earth is a giant magnet. And so we've developed the compass to help us guide us based on the field lines of the magnetic field of the Earth. And we've learned that all magnets in the northern, all magnets everywhere, point towards the north, point towards the geographic north. All right, when you pull a compass out, it's pointing toward the North Pole on Earth always. The thing is, the compass itself is pointing with the field lines. So it's pointing in a direction that the field lines want to go. So this is always pretty confusing for people. If it's pointing with the field lines are always pointing and away from the north and towards the south. It's always trying to get towards the South Pole. That's the South Pole of the magnets. See, this is why it's confusing. So what am I trying to say? A compass is pointing north geographically, but it's pointing south magnetically. It's pointing towards the south magnetic pole. So this is really confusing, but this is a good drawing of it. This is basically showing you that the South Pole of the magnet is at the North Pole of the Earth, and the North Pole of the magnet is at the South Pole of the Earth. And And that's the only way, or only reason why the compass is always pointing towards the north, is it's following those field lines that come out from the South Pole geographically, out from the North Pole magnetically, going around and coming back to the South Pole magnetically, North Pole geographically. I probably have you horribly confused now. All right. Main thing, compass follows the Earth's magnetic field. It points along the field lines. Okay. The geographic and magnetic fields, or magnetic poles, are opposite of each other on Earth. So, how can I make a magnet? What if we had to actually produce a magnet? A couple quick ways that could be done is basically, it is possible to rub a metal with a magnet. All right, when you rub a metal with a magnet, basically what you're trying to do is you're trying to encourage those electrons to basically all start pointing the other way. So if I keep pushing a magnet over and over again on a metal, it's possible to switch those electrons around and all start making them point the same direction, therefore making it magnetic. Another way is to place it in what we call in a DC electric current, which we did on the prior video. Basically forcing those electrons to all go one direction, and as they're kind of spinning by it, basically it's like a top. They basically spin by the top, making it everything try to spin that way, and therefore creates, again, all the arrangement of the electrons to be in the same direction, and therefore magnetic. All right. Now we're going to come back to that because that's called an electromagnet as well. If we want to break a magnet, if we want to destroy a magnet, basically, I'm not just saying split it in half, but stop making it magnetic, you can drop it repeatedly. All right. It's kind of silly, but if you basically keep on smashing it, again, if all those electrons are in the same direction, but you keep on jarring it, you keep on shaking, you keep on really smashing it, you might have some of those electrons basically flip back in the other direction because they're jarred. They can't keep on spinning one way because you're kind of knocking them out of alignment and making them start spinning the opposite way. All right. You could also heat it up. Similar idea, those electrons start going even faster. Again, they're not all spinning in one spot. All right. It's not like they're staying in place. They're all spinning but constantly moving around and around and around. So if you heat them up, you're making them move even faster. They might collide. That might make them start spinning a different way and therefore breaking the magnet. Okay. Another thing you can do is you can throw them in an AC current. As we talked about with an AC current, you're basically making electrons go one way and then the opposite way and then one way and then the opposite way. And that can cause the spinning to get out of alignment. Okay? So basically anything, the big thing to kind of think about is magnet involves electron spin. And if you can mess with how they spin, that's whether you can make it into a magnet or not into a magnet. So then we have a special type of magnet called an electromagnet. An electromagnet is something that you can turn the magnetism on and off. This is actually a very, very common type of magnet. You're using them probably all the time. But this is something based on whether electricity is running through it, a current is running through it, we can make that object begin to be magnetic or not magnetic. So an electromagnet is essentially made up of an iron or metal core that you just wrap in wire. All right? That's essentially all that it is. It's a piece of metal that you wrap up with a wire and then run an electric current on through it. All right? So when a current is running through the wire, the object becomes magnetic. When the current is not running, there's no magnetism. So these are all the big junkyard magnets. The whole idea is you put the magnet down close, you flip the switch, it becomes magnetic, pulls the stuff, can hold it, carry it, and then you want to dump it somewhere else, turn the magnetism off. Okay? So it kind of is forcing all those electrons in one direction and then basically telling them to stop. All right? So how can I make an electromagnet stronger? It's actually pretty simple. I used to do a little quick experiment with this where we essentially just grab nails and you just wrap the wire around the nail. The more times you coil the wire around it, the more turns you have on it. So if we have a nail and we just wrap it, if I only wrap it like 4 times, it will become magnetic. But then if I wrap it basically like 6 or 7 times, it will become more magnetic. That's all we mean. You just wrap it more. Okay? So that'll increase the strength of the magnet. The other thing, you throw more current into it. If you throw more current in there, it's again all these little electrons all spinning around. I always compare it to like a Hot Wheel set with the little spinning wheels where you can throw the Hot Wheel car in, and when it hits the spinning wheels, it zips it around faster. That's basically the idea too, is you're zipping those electrons and making them all spin faster and faster in the same direction. The last thing you really need to know is, where do we use electromagnets? This, I always tell everybody, this was something I always struggled with when I was in school. I don't know why I could never pick out in that question what uses electromagnets. The thing that I just should have remembered is anything that's producing sound has an electromagnet in it. All right? Any speaker, headphone, sound device has an electromagnet in it. And that is because that's what's creating the sound. When you're turning on and off the magnet, the speaker is either expanding out or it expands in when or it pulls in when the magnet is off. It's one or the other. But basically the idea is the speaker is constantly going back and forth, which then pushes the air and creates sound. All right, that's supposed to be my speaker if you have no idea what that was. All right, so anything with that produces sound has an electromagnet. Motors. A motor has an electromagnet. It's what helps spin. It's what helps change the electrical energy and the mechanical energy, and vice versa. Generators use electromagnets to change mechanical energy into electrical energy. Basically, in both of these, you have some sort of a little like metal arm that's in the middle that can rotate, and then you have wires wrapped around it, and essentially, based on what those, like the direction the current's going, it can make that middle metal piece spin in a particular direction, creating mechanical energy. Vice versa, if you have a magnet that's in the middle and you spin that around within wires, it actually can create electricity, which would be a generator. All right, so I think that's basically it. What we got here is, again, magnetism, created by essentially the arrangement of the electrons, the spin of the electrons. It creates a force, an attractive or repulsive force, depending on which poles, north and south, you have near each other. It creates a magnetic field, which always points from north to south. We have ways to create and destroy magnets, as well as the object called an electromagnet, what it does. It's something that you can control, whether the magnetism's on or off, and you have these different devices that have electromagnets in them. So that's about it. Thank you.